Is it visible to you? The screen is visible.
Yes, sir. Yes.
System performance. We have started some initial discussion. Or maybe someone is trying to join. Oh yes. Okay. We have started some initial discussion, and that was basically regarding the what I wanted to see how much is your at what level we are. Basically, since I shall be discussing all these things, so I wanted to interact with them initially. That I do in every class. So that was there. Now today I am starting with the course, starting with the power system performance course. Okay. So power system performance, basically, what you know, what is the function of a power system? Function of a power system is to supply power, and not only supply power, that power has to be reliable, has to be cheap at the same time. That means we can say that the perform the function is to supply good quality of power. I shall define later on what we mean by the term good quality power to the consumer at cheap rate. That is important, obviously, in such a way that the security of the system is maintained. So basically, I have mentioned about three different terms. One is good quality, then cheap rate, and security of the system. Now let us see how we define all these things. Okay, how we define all these things. When we talk about power quality, basically the power quality is determined by the voltage. That means quality of voltage, whether the voltage is as the value or not. Whenever in any power system, if certain voltage is declared, this should be the available voltage. This is the rated voltage. All equipments are actually designed and operated at that voltage. So whether that voltage is maintained or not, magnitude of voltage, that is important. So that is one indicator of power quality. Next is frequency. How stable is the frequency? Every power system has certain declared frequency. In our power system, declared frequency is 50 hertz. So frequency has to be as close as possible to 50 hertz. We shall see later on what will happen if the frequency is not maintained at this voltage. We have mentioned regarding the voltage, you know that in power system there are different levels of voltage. Okay, at the generation voltage is lower, then it is stepped up. At transmission it is high voltage. When I use the power, then again the voltage is much lower. Okay, so all these levels are there, but whatever is the voltage level at any point, it has to be as close as possible to the declared value. You cannot afford to have much deviation from the declared voltage. These therefore will indicate the quality of power. Okay, then wave distortion. Then whether basically the power is generated from synchronous generator. This was the what was happening in the power systems starting from the beginning and up to this time. Okay, but recently what happened? There are other things, other form of generations are coming in. Different types of loads are coming in. Because of these loads and different types of generation, there is a possibility that voltage will no longer be purely sinusoidal. So that is another indicator whether the voltage is sinusoidal or not. If the voltage is sinusoidal, then we say that the power quality is good. If it is not, some distortion is allowed because there is some declared value of deviation, that is permissible value of deviation, that is allowed. That means the quality of voltage waveform, nature of voltage waveform should be sinusoidal, and a small deviation from it may be permissible as declared by the different regulating authorities. Okay, and fourth one is the continuity of supply. You must get power whenever you want to use it. That means it has to be available all the time. That means the supply has to be reliable. Okay, so all these things basically determines what is the quality of power. You will be asking question. If you cannot understand any point, you please ask me question because that interaction is important, that is necessary. Okay. Now let us come to the second point, that means the supplying power at cheap rate. How you can supply power at cheap rate? For supplying power, obviously your total investment in the power system has to be lower. Okay, that requires that the design of the power system has to be optimum. Whenever you are designing a transmission line or any equipment, generating equipment, transformer, that means the total transmission, generation, and distribution system has to be operated in an economic way, has to be designed in an economic way. Okay, so design of equipments or system equipment related to power supply and distribution and all these things should be optimally designed. Okay, and the generation also has to be economic. That means you are generating power mostly from synchronous generators. You can say that in any power system, except very few, until now, the proportion of or the contribution of power is mostly from synchronous generators. And synchronous generators, you know that, may be actually rotated by steam turbine or maybe ideal turbine. When it is ideal turbine, then cost of generation is not that much, except the cost of the working personnel and initial investment. Okay, but when we go think about the generation from thermal power station, that is by generation of steam, then comes the question of cost of fuel. Okay, and that fuel is costly, and you have to actually generate power in such a way that the cost of fuel is minimum. That means generate power, but generate in such a way that the minimum amount of fuel is needed. How that can be done, this we shall see later, and this also will be discussed. That means for supplying power at cheap rate, you have to generate economically as well, and obviously you have to operate your system in the most possible efficient way. That means the management of system is therefore very important. Operation of the system is important. Management of the system is also important. Okay, so this is regarding the supplying of power at cheap rate. Then comes the question of system security. What is the system security? System security means whether the system is available or not. It means the proper system is available. So availability of the system to withstand unplanned disturbances. When disturbances occurs, what will happen? Say a fault has occurred. Now, do you understand what is a fault? Fault means basically an unwanted operating condition. Say a transmission line is there. There may be a connection from one of the line to ground, maybe through three branches, maybe through the tower of the transmission lines. Okay, maybe two of the lines are somehow shorted. So these type of events, that means a short circuit, we say, these type of events, what they will do, because of this short circuit fault, a large current will be flowing. Okay, a large current will be flowing. Why the large current will be flowing? Because otherwise there was very high impedance. Now a low impedance path is created. So from the supply to transmission line, a ground path is created. Say if we think about the line to ground fault, then from conductor to ground there is a low impedance path created. So total voltage is now impressed upon the upon this impedance only. That means transmission line impedance and then ground to generator again. So obviously the impedance is low. So as a result, what will happen? A very large current will flow. Okay. This large current may cause damage to the equipment of the power system, may burn out the conductor, may burn out the insulation of the generators and all these things. Therefore, this fault has to be isolated from the system as fast as possible. And for that purpose, there are relays and circuit breakers installed in power system. Okay. What is the function of relays and circuit breaker? Relays will actually identify the occurrence of such unwanted event, maybe in the form of some deviation of current from normal value, deviation of voltage from normal value, deviation of frequency from normal value. These are the, you can say, the methods of identifying the occurrence of unwanted events in power system. So relays do this function. Okay. So after identifying the faults, the next function will be done by the circuit breaker. Circuit breaker will then disconnect the faulty part of the power system or say faulty component of the system from the system. That means at the both ends of the equipment, say transmission line. So from both end of the transmission line, there are circuit breakers. So immediately after the fault is identified by the relay, circuit breaker will be informed about the occurrence of the fault and the circuit breaker contacts will be opened. Circuit breaker basically is a switch with some other, you consider some other facilities inbuilt in the circuit breaker. So basically it is a switch and that switch will be opened. As a result, transmission line will be disconnected from the system. So fault will no longer be there in the system. So normal operation will be possible. Okay. But what will happen? You'll see that after the finish the course, you'll see that disconnection of such a line is sometimes very detrimental to the power system. Why? Because a large power was flowing through this transmission line. Okay. And whenever a large power flow is interrupted, a sudden shock is created in the power system, and the generators in power system, basically the synchronous generators, they may not be able to withstand that shock. And as a result, what may happen? The system operation may be hampered, the system may collapse totally. That also may happen. Okay. So therefore, in system security, what we do, we basically see what will happen in the system if a certain component is disconnected from it. Okay, if a transmission line is disconnected from the system, what is the impact of that disconnection on the system? If a generator is disconnected, what is the impact of that disconnection on the system? These things are actually always monitored, always determined what will happen. Okay. And if you can identify this thing properly, if you can do this properly, then what may happen? You can take preventive measures so that after this disconnection also, the system may be maintained in normal working condition. That is called the maintaining system security. Okay, so a power system must have a very good security management system, security monitoring system, so that normal operation of the system may be maintained as long as possible. Because if the system fails, then consumers will not get power. If the consumers do not get power, then what happens? The power utility will not get the revenue from it. Not only that, if the system collapses, then a very, very long time will be needed to restore the system to normal operating condition. Actually, in 2012, in Indian power system, is similar such event has taken place. Okay, almost the total system was collapsed after the disconnection of a transmission line, after the disconnection of a 400 kilovolt transmission lines at the northern part of our country. Okay, this thing happens, and these type of events happen not only here in every power system. These occurrences of this type of events are there. Okay, and these are to be prevented for secure operation to ensure the security of operation of our system. Okay, that is basically the security of the system. Okay, so in this particular course, however, we shall not be mentioning or we shall not be discussing about the system security. We shall not be discussing about the so-called efficient operation, optimum design, all these things. Mainly the voltage and frequency maintenance and economic operation somehow will be discussed here. And another thing is also there, that is regarding the integrated operation of power system, that we have actually mentioned about the collapse of the total system. Collapse of the total system is actually associated with the so-called stability of the power system. So we shall be discussing about the stability of the power system also. What is stability? Basically, it is the ability, in the conventional meaning, stability of power system means the ability of the system to maintain normal operation after a large disturbance. Okay, ability of the system to maintain normal operation after a disturbance. Okay, stability in the past was actually meant in this way. That means this is the stability of synchronous machine. But later on, the stability actually, the definition of stability rather has changed because there may be the problem of maintaining normal operation of the system. The system may collapse not only because of these issues, not only because of the incapability of synchronous machines to maintain synchronism, but or the inability of the due to the inability of the system to maintain proper voltage. Okay, if you cannot maintain proper voltage, then also system may be collapsed. Okay, so there's aspect also we shall be discussing. So in this course, basically, I shall be discussing with the this mostly on frequency issue, a part of maintaining voltage that also I shall be discussing, and also I shall be discussing with the maintenance of system stability. So stability, then frequency maintenance, and also a part of maintaining voltage that is by using generators that will be discussed in this part. And regarding the efficient operation of the system, something will be discussed in the other half. Okay, Professor Sunita, Madam, perhaps will be taking that part. Okay. Now, coming to the uh, issues of frequency maintenance, frequency and voltage maintenance. Let us now see why frequency control is necessary. Okay, up to this, is it clear to you whatever I have discussed, or any question you are having? বলো কোনো কোশ্চেন আছে এখানে এই অবধি?
No, sir.
Okay. No, sir. Let us see why the frequency control is necessary. Why frequency has to be maintained at constant value. Okay. What happens if you if the frequency is not maintained? Then what happens? Speed of consumers plant changes with supply frequency. Okay. Production process gets hampered. Consumer plants. Consumer plants means, say, what are the consumer plants? Basically, we are talking about some industrial system. Okay, industrial motors. There are a lot of, say, induction motors out there. So what happens if you change the supply frequency of an induction motor? Can you say what will happen to the speed of induction motor if the supply frequency is varied? What will happen? Say normal frequency is 50 hertz. Due to some reason, say frequency is not 50 hertz, say it is 49 hertz or say 49.5 hertz. So what do you expect to happen to the speed of the induction motor under the reduced frequency?
The speed will change.
Change means it will increase or
reduce, sir, reduce.
It will decrease. তাহলে কি হবে? If the frequency decreases, speed of the motor will decrease. Then speed of the motor will decrease means speed of the production process also will be deviating from the normal. Okay, as a result, quality of the product will be difficult to maintain. So that's why you must maintain the frequency constant. Similarly, if the frequency increases somehow because of some reason, then also speed of the consumer process, because motors used in mostly the AC motors, basically induction motor, their speed will change, and as a result, the quality of the production process, efficiency of the production process will be disturbed, will be hampered. So, what this is one of the reasons why frequency has to be kept constant. Now, synchronous operation of that also requires the constant frequency operation. You know that synchronous generators. Why they are called synchronous? Because they all operate synchronously. Okay, they must maintain the constant speed of operation, synchronous speed of operation. What is the synchronous speed of operation? Depending upon the frequency, depending upon the number of poles of the generator, there is a frequency, there is a speed. That speed we call the synchronous speed. So all generators must operate at synchronous speed. So say some of the generators are running at synchronous speed, some are not. Then what will happen? The frequency of the system will change. If the frequency of the system changes, then maintaining synchronism of the power system may become very difficult. Okay, there will be unwanted operation in the power system. In what form there will be unwanted operation means frequency of the system is changed. Means the generator, say incoming generator, say or one of the generator that is say running at synchronous frequency. Okay, but the system frequency is say not synchronous; it is say above synchronous. Imagine that synchronous system frequency is above synchronous. Then what will happen? That you see that with respect to the system, frequency of the generator is changing. Okay, it is different, so it is changing. That means the angle between the two voltages, that means the voltage of the system and terminal voltage of the generator, angle between these two voltages will actually change. If this angle changes, what will happen? The power from the generator, the system, it will also change. Power output for the generator to the system, that also will change. It will not only change, it is continuously changing. Therefore, what will happen? Sometimes the the power will flow from the generator to the system. At some other time, power will flow from the system to the generator. As a result, there will be fluctuation of power flow. And this fluctuation of power flow will cause damage to the synchronous operation of the power system. As a result, you may have to disconnect your generator from the system. So you see that the synchronous operation of the system is very, very important. And to maintain synchronous operation, it is essential that the system frequency must be kept constant, must be the declared frequency. So you cannot allow the frequency to change. You have to control it, you have to regulate it, you have to maintain it at the declared value. Okay. Then there is a third reason. Active power consumption of a load depends upon supply. This point, active power consumption of a load depends upon supply frequency. Can you understand this point? Why the active power consumption of a load will depend upon the supply frequency? Any idea or any explanation to it? তুমি বলতে পারবে কেন অ্যাক্টিভ পাওয়ার কনজাম্পশনটা ফ্রিকোয়েন্সির উপর ডিপেন্ড করবে? লোড কতটা অ্যাক্টিভ পাওয়ার কনজিউম করছে, that also depends on the frequency of the supply. How it depends upon that? Anybody having any idea?
স্যার সাপ্লাই ফ্রিকোয়েন্সি চেঞ্জ হলে স্যার ওই ইম্পিডেন্স গুলো চেঞ্জ হয়ে যাবে, সেই জন্য কতটা পাওয়ার ড্র করছে মানে কারেন্ট ড্র করছে সেটা চেঞ্জ হয়ে যাবে, পাওয়ার ফ্যাক্টর চেঞ্জ হয়ে যাবে, ওই জন্য অ্যাক্টিভ পাওয়ার কনজিউমও চেঞ্জ
হয়ে যাবে। So there is another aspect. So what you see, if the supply frequency changes, then obviously inductive reactance changes. Mostly in power system, we know that reactances are mostly series reactances are inductive and shunt reactances are capacitive. Okay, so system reactance will change because of the change in reactance. What will happen? The total impedance will change, current flow will change, and therefore that will have some impact on the power consumption of the load also. Okay, because of the change in current. There is another aspect also. Say again, we are coming to that induction motor. Say you have an induction motor load, and say that motor is basically is driving a conveyor belt, and that conveyor belt is actually carrying some mechanical load. Right? So, এরকম একটা conveyor belt যদি থাকে, obviously what the conveyor belt will be doing, it will be rotating, it will be shifting its location. Okay, it is circulating, and as a result, what will happen? The load that has been put on that will be just 1 minute. একটু পরে ফোন করছি আমি, হ্যাঁ, একটা ক্লাস করছি। So what will happen? The that conveyor belt basically it is rotating and carrying some load, and that load, say it is constant. Okay, so we have put a fixed amount of load on conveyor belt. Now, if the frequency changes, then what will happen? Speed of rotation of the conveyor belt also will change because the speed of the induction motor will be changing. Okay, so you see that if the speed increases, the motor will be rotating at a higher speed. The load is fixed on the conveyor belt. That means if the same load is now transferred more rapidly compared to the previous time when the frequency was normal. Is it clear? So what will happen? What will happen to the power consumption? Power requirement will be more in this case. Is it clear? That is,
Yes, sir. Yes.
is it clear or not?
Yes, sir.
That means if the frequency increases, say, then speed of induction motor will increase. Now, if we assume that this induction motor is basically connected to a conveyor belt, which is carrying a fixed amount of load, mechanical load, now at normal frequency, the speed of rotation or speed of displacement of the conveyor belt was a certain value. Now, with increased speed, due to increased frequency, speed will increase, therefore, shifting of load will be much speedy. As a result, what will happen? Obviously, power consumption will be more because same load it is carrying at a faster rate. Okay, therefore load will increase, power consumption will increase. Similarly, if you assume that speed is decreasing, then the same load also will be carried by the conveyor belt at a uh, much at some slower rate. A slower rate means obviously power consumption also will be less. That means you can say that this type of load will consume more power at higher frequency, less power at lower frequency. So if this happens, what will happen? You cannot actually estimate what will be the power demand of the system. Unless your frequency is known, frequency is constant, you cannot estimate properly what will be the total power demand of the system. And this estimation of power is very, very important. Okay. Therefore, for these three reasons, the frequency control is necessary. That means consumer process, you see that depends upon the speed, depends upon the frequency. Not only the speed, quality also will depends upon the frequency. For synchronous operation of the system, the frequency has to be kept constant, and the consumer active power demand that also depends upon the frequency. Okay, so for all these reasons, the frequency has to be kept constant in power system. Is it clear or not? The reasons, is it clear? Would you understand?
Yes, sir.
Okay. Next, come to the voltage. Why system voltage has to be controlled? Okay. Now you see that power apparatus are designed to operate at declared voltage. Okay. Efficiency and safety of equipments are hampered if proper voltage is not maintained. Whatever equipment you actually design, that you design to be operated at a declared voltage. Okay. So what will happen? If you cannot maintain the voltage, then say somehow the voltage increases compared to the declared value, then your equipments are designed to be operated at rated voltage. Now, if the operating voltage is higher than the rated voltage, then what will happen? There will be more voltage stress on the insulation of the equipment. As a result, insulation will get damaged. So, life expectancy of the equipments will be hampered because of the inability of your system to maintain voltage. At the same time, if you cannot maintain the voltage, then efficiency of operation of the system will not be maintained. Okay, so voltage is not normal, it is much less. So obviously, your equipments, then what will happen? If the voltage is less, obviously then stress will not be there. But at the same time, what will happen? The efficiency of the operation of the equipments will be hampered. Okay, so for maintaining proper safety, life and safety of the equipments, voltage has to be kept constant, and also for maintaining efficient operation, okay, to have the desired work done by the equipment, power system equipment, you must maintain the constant voltage, declared voltage at the nodes, at different nodes of the power system. Okay. Then motor load takes more current at reduced voltage, causing increased voltage drop and thus aggravating the voltage condition. Motor load. Motor loads are known to be constant power type load. Okay, most of the motor loads are known to be constant power type load. That means they require constant power for their operation. Okay, if they require constant power at reduced voltage, what they will do? If the voltage is not the declared voltage, okay, they have been designed to operate at a declared voltage. Now, if you cannot supply that declared voltage to the motor terminal, then what will happen? These motors, since they require constant power for their operation, they will draw more current to maintain constant power. That means at reduced voltage, they will be drawing more current. More current means obviously voltage drop in the system impedance will increase. That means this current is actually entering into the load from the generators of the power system. So from the generators to consumer point, there are different impedances connected in series. There are impedance of the generator, impedance of motor, impedance of transmission line. All these things are there. Maybe for reduction of voltage, there is again a transformer is there. So in all these impedances, because of increased current flow, there will be more voltage drop. More voltage drop means at the consumer end, there will be further reduction in voltage. And since the voltage reduction, more voltage is less, sorry, more voltage drop occurs in the system, terminal voltage of the load will decrease further. As the terminal voltage is decreasing further, this motor load again will consume more current. That means current drawn by the motor from the system will increase further. Because of increased current, again the voltage drop will increase. So in this way, there will be a cascading effect. Okay, and because of cascading effect, there may be continuous reduction of voltage at the consumer end, and this may finally lead to the problem of so-called voltage instability of power system. Okay, is it clear? That means since the motor loads are known to be constant power type load, at reduced voltage, they will draw or they will consume more current. Since they are consuming more current, what will happen? There will be further reduction in the system in the voltage at the motor terminal. Okay, because of reduction in the voltage in the motor terminal, there will be further increase in the current drawn by the motor. This will lead to the further reduction in the terminal voltage. As a result, it may so happen that the voltage collapse of the system may take place because due to the continuous reduction in voltage, it may so happen that system will not be able to maintain its proper operation. As a result, system may collapse. Okay, that means the integrated operation of the system may collapse. If this type of situations happen at a single node, then it is propagated to other nodes also. That means if voltage collapse takes place at single node, then similar events will take place at other nodes also, unless this is arrested by the protection system in the right time. Okay, so for this reason, we must maintain constant voltage at the consumer terminal. Means maintaining constant voltage at the consumer terminals require that it will be maintaining constant voltage throughout the power system. Is it clear up to this why voltage has to be kept constant? Or any further any question you are having?
No, sir.
Okay. Then now let us see why the frequency changes. We have mentioned why the frequency has to be kept constant. Now let us see why the frequency changes in power system. Okay. The reason is basically the unbalance between the active power generation and active power demand. That means load on the system is continuously changing. If there is more power demand, you have to supply more power to the system. And if you cannot supply more power, then there will be a reduction in the frequency. How it happens? Let us see. Let us consider this situation. This showing in the left-hand side figure. We are showing a generator here, and as if two loads are connected here, the loads impedances are shown to be Z1 and Z2. Now say this load, load 1, basically say whose impedance is Z1 is now switched on. If this load is switched on with load Z2 disconnected, then say current drawn by the load is I1. Because of current I1, say what is the torque, electrical torque output of the generator? Say it is T1. and input torque is T in. Input torque indicated by T input, T in, and electrical torque output is T1. Obviously, this torque output depends upon the current drawn by the load I1. Now, if and when this current is drawn by the load I1, obviously motor is delivering this current I1. Okay. Now, assume the situation when in this condition when happens when this torque is T1, input is T in. So here torque input to the system is equal to the torque input to the generator is equal to the torque output if the system is stable. So let us assume that with this load connected, the system is stable. So input torque completely matches with the output torque. Okay. Now imagine the situation when the second load with impedance Z2 is also switched on. Okay, it is also switched on. So what happens? This load, say this voltage is, we can say this is more or less constant. So as soon as this load is switched on, this load Z2 is drawing a current I2. Okay, so what is the total current drawn from the generator? Now it is I1 due to the previous load and I2 due to the present load. So total current is I1 plus I2. As a result, since the current delivered by the generator is increasing, then torque delivered torque output of the generator also is increasing. It is T2. Obviously, this T2 is greater than T1 because we have not changed the input torque to the system. Input torque will change if we change the input to the generator. What is the input to the generator? In case of steam turbine, it is the steam input. In case of hydroelectric turbine, it is the hydro turbine. So immediately with the increase of system load, torque in the torque input to the generator cannot change. Do you understand this point? Why the torque input to the generator will not change immediately after a change in the load in the system? Can you get this point or not? বলো একটা load connect করা হয়েছে immediately it will draw more current. As a result, torque output of the generator will increase, but torque input to the generator remains at its previous value. Now the question is why? Can you understand this point? Why the torque input will not change immediately?
Yes, sir, because the prime mover is being rotated so that by for example hydro turbine, that water speed that is fixed, so torque input will not change.
Actually, how much water will enter into the turbine, or how much steam will enter into the turbine, that is dependent upon the opening of the turbine valve. Okay, what is the opening of the turbine valve? That means to allow more steam into the turbine or more water into the turbine, you have to increase the opening of the turbine valve. Okay, you have to increase the opening of the turbine valve. Okay, since actually your input system do not know, actually input system basically what are the input system? That means the fuel control, water control, this system, they do not know actually that the load has increased. Because how they will know? Because loads are in the power system. Okay, in power system at a certain location, the consumers or the customer, they have increased they have switched on their load. Obviously, at the power station equipment cannot know this. So they will keep the opening of the turbine valve fixed at their previous value. From measurements made in the turbine, made in the boiler, okay, the system will be able to know later on that there is a increase in demand in the system. How they will know that? Obviously, they will know it by measuring the frequency, by measuring the speed of the generator. Okay, so initially what will happen? Initially, after the increase in the system load, there will be change in the speed, there will be change in the frequency. This frequency will be measured by the system and then they will know that there is an increased demand, then they can increase their opening of the steam valve or water valve. Okay, so before that, system input cannot change. So therefore, what will happen if the load increases? Immediately there will be increase in the torque output of the system. Okay, but torque input will remain same. It will be as before. Since the output torque exceeds the input torque, so what will happen? Torque output is more than torque input means speed of the generator will decrease. Are you getting? Is it clear? That means immediately the torque output increases, but torque input remains same. So as a result, speed of the generator decreases. All right. So therefore, since the speed of the generator decreases with the increase in load, what happens? The frequency falls. Frequency decreases. Why the frequency changes? Why the frequency decreases? What is the primary reason? Therefore, we see that if we could increase the input to the generator, if we could increase the input torque, there, or you can say that if we could increase the input power to the generator, then the speed change could have been prevented. But we cannot do this because we don't know at the system, at the input end of the generator, we don't know that the load to the system has been changed. So as a result, what happens? There is an unbalance between the active power input to the generator and active power output from the generator. Just 1 minute. স্যার আমি একটা ক্লাস নিচ্ছি, একটু পরে ফোন করছি আমি। হ্যাঁ হ্যাঁ ওকে ওকে ঠিক আছে স্যার হ্যাঁ okay. So there will be an unbalance, basically an unbalance occurs between the active power input to the generator and active power output to the generator. Why this unbalance occurs? Basically we are not allowing more steam. More steam entering means the ability to do more work is there. That means the input power is increasing. Okay, since we are not allowing that power to increase, the speed of the generator decreases, because with the addition of the second load, with the switching on of the second load, there is more power output from the system. Now the question may be, where from this power is coming? How the generator is supplying this power? Basically, this power is being supplied by the generator from the stored kinetic energy. The speed is changing, speed is decreasing means stored kinetic energy of the generator, stored kinetic energy in the rotor of the generator is changing, it is decreasing. Am I clear? That means as soon as you are switching on a load, you are getting power. But where from the generator is delivering this power? This power is being delivered at the cost of speed of the generator. Speed of the generator decreases, and because of this reduction in the speed of the generator, there is release of the stored kinetic energy of the generator, stored kinetic energy in the rotating mass of the generator, that means rotor of the generator, and as a result, the load that has been switched on is getting power from the generator, but it is at the cost of speed of the generator. If we could increase the power input to the generator simultaneously with the increase in power output, that means with the increase in addition of the load, then the reduction in the speed would have been arrested. But since this cannot be done, it will be happening on. Oh, hello. Sorry. Okay. So it was interrupted for some time. Okay. So what happens with the increase in demand, increase in load, the power output of the generator increases. Where from this power is coming? It is coming from the stored kinetic energy of the rotor of the generator, and therefore you see that since the kinetic energy is reducing, means the speed of the generator is decreasing. So with the increase in demand, increase in the load, speed decreases. Why the speed decreases? Because the input to the generator cannot be increased simultaneously. That means you can say that an unbalance between the active power generation and active power demand. Generator cannot generate more power. Why it cannot generate more power? Because it is not getting more power supply. Mechanical power supply is not changing. That's why it cannot increase its power output. Okay. So an unbalance between the active power generation and active power demand is the reason for frequency change. And similar thing happens in case of load reduction. In case of load reduction, you say these two loads were connected. Now, if you disconnect one of these loads, then what will happen? Torque output will decrease immediately, but input torque will remain same. Since the input torque is greater than output torque, speed of the generator will increase. Speed of the generator will increase means basically the frequency of the system will increase. And why this frequency is increasing? Because active power input to the generator is now more than the active power output from the generator. So we can say that the basic reason for the variation in frequency is the unbalance between the active power input and active power output of the generator. Is it clear or not? Why frequency changes? Clear?
Yes.
Okay.
Yes, sir. Yes.
All right. Next, come to the issue of voltage variation. Why the voltage varies? Obviously, the answer perhaps is known to you, because if the load changes, obviously current drawn by the system will change. Since the current drawn by the system changes, then voltage drop in the system impedance also will change. If the voltage drop in the system impedance changes, then what happens? Obviously, at the consumer end, voltage will change. Okay, so the answer is known to us there. Voltage varies because of the variation in the current drawn by the load, or you can say that because of the variation of the connected load. Now the question is, the load is having two parts. One is the active power load, another is the reactive power load. Okay, load power is active, at the same time a portion of the load power is reactive. Now we want to know which part of the load is more responsible for voltage variation. Could you get my point? Because we shall be now investigating, we shall be now examining which part of the load is the primary reason for, or primarily responsible for the variation of system voltage. Because why it is important to know? Because then only we can control the voltage properly. We can take corrective measure properly if we know the cause. So for that, let us assume that we have a very simple system consisting of a generator supplying power to a load through a transmission line. So at the load end, voltage is V2, at the generator end, voltage is V1, and this is the transmission line. We are assuming that this line basically that we are showing here, it includes everything, including the transformer also. Okay, because generator voltage and load voltage, they will not be same, but we are not showing this here to actually keep the system simpler. We are not trying to enter into complicated things initially. That's why, to keep the things simple, we are assuming here that we have a transmission line only, but basically we are assuming that the impedance of the transformers at the sending end of the generator and at the receiving end of the line also are being included here. Okay, why I am making this comment? It will be actually clear now when I discuss this thing issues. Yeah. Okay. Now assume that this voltage V1 is constant. I am assuming that voltage V1 is constant. This assumption is a very correct assumption. Why it is a correct assumption? Because later on we shall see that in any power system, generator terminal voltages are always kept constant. Okay, always in any power system, how the system is operated, it is operated basically by maintaining constant terminal voltage. You must maintain constant terminal voltage because that is that makes the voltage control simpler. So we shall see these issues later on, but let us, for the time being, let us accept this point that this voltage will be kept constant. V1 is kept constant. And since in AC system, in any calculation, you must actually measure the, you must include the phase angle also. Say for phase angle measurement, we are considering this voltage as the reference voltage. So V1 is reference voltage. So that means V1 is the magnitude at an angle of 0 degree, and V2 will be a voltage which is making an angle with V1. Okay. Say P plus JQ, active power is P and reactive power is Q. So P plus JQ is the power flowing, power drawn by this load is the power basically delivered here is P plus JQ. Okay. So what will be V2? This voltage at the load end, V2 will be this voltage V1, generator and voltage minus I into Z. I means the current flowing through the line. It is shown here, current flowing is I. And Z is the impedance of the transmission line. Impedance of the transmission line is Z. Okay. Now, from the here, let us calculate the current value. What is current? P plus JQ is the power flowing. So how can we write P plus JQ in terms of voltage and current? We are actually say measuring the power here. It is P plus JQ. Okay. If it is P plus JQ, what is the current delivered by the generator? Anybody? What is the current delivered by the generator? It is written here. Can you explain why it is written in this way? Why we are writing I conjugate as P plus JQ by V1? Means that I am writing P plus JQ equal to V1 into I conjugate.
Because sir, it is the summation of active power and reactive power, both are there. So that's why we are writing V1 I conjugate. If we are,
Can you please repeat? I could not follow clearly.
so here we are taking the reactive and active power both. So that's why we are writing VI conjugate. If we are taking only active power, then we should take VI.
No, my question is why I am not writing P minus JQ equal to V1 I conjugate, or I am not writing P plus JQ equal to V1 conjugate I. Why? V1 into I conjugate is written as P plus JQ. Okay, this is my question.
Sir, because when we consider complex power equal to VI conjugate, then we consider inductive.
Yeah, basically what happens if we assume that inductive power, that means reactive power Q is positive, then we have to write VI conjugate at the expression of power. That means P plus JQ. Assume that inductive reactive power is positive, we have to write V into I conjugate. If we write V conjugate I, then the expression has to be changed. It will be P minus JQ. Okay. Why this is so? Because basically we see that V1 is V1 with respect to a certain reference, say V1 at an angle of alpha. Say I is say I with respect to same reference at an angle of beta. Okay. So I am writing, say, because I cannot write here, so I am simply telling you this. Say V1, say it is, here we have taken this as reference for better understanding. To generalize the discussion, let us assume that V1 is measured, angle is measured with respect to a global reference, with respect to common reference. Say it is V1 at an angle of alpha, and I is measured with respect to the same reference because reference has to be same. Say I is I at an angle of beta. So what is active power? Active power will be BI cosine of power factor angle, cosine phi. So you see that here to get active power, you must write V1, then I conjugate, because conjugate will make the angle of current negative. Okay. Then it will be voltage, angle of voltage minus angle of current, which is nothing but the power factor. Am I clear? Is it clear? So if you write V1 is V1 at an angle of alpha and I is I at an angle of beta, you see that active power will be Vi, then cosine of phi. What is cosine of phi? Phi means the angle between voltage and current. In our case, the load is mostly inductive, so current should lag the voltage. Okay. And how you can represent this? How can measure alpha minus beta? It is the power factor angle. To get minus beta, you have to take the conjugate of I. That's why we write V into I conjugate while we write P plus JQ. Okay. All right. So I will be, I conjugate will be, you see that from that P plus JQ by V1. Okay. For our case here, V1 is the reference phasor. Okay. V1 is the angle is 0 here because this is taken as the reference. Now, therefore, I will be how much? It is I conjugate is P plus JQ by V1. So I will be equal to P minus JQ by V1. Since V1 is reference, it is not changing here. It is remaining same. Its angle is 0. So positive 0, negative 0 does not mean anything. It is 0. So each becomes P minus JQ because of conjugate is now the total current I, conjugate of conjugate. So P minus JQ by V1 is the expression for current. Okay. Now you find out the V2. What is V2? V2 is V1 minus I into J. So V1 minus I is P minus JQ by V1, I into Z. What is Z? Z is R plus JX. Right? Resistance plus J times of inductive reactance. All right. But what happens? We are assuming that our system is a high voltage system because whenever we shall be talking about frequency control, whenever we shall be talking about voltage control, as if we are discussing about the high voltage part of the power system. Okay, we are discussing about the high voltage part of the power system, and in the transmission system, high voltage system, we have mentioned. I have discussed this in my next class, previous class, that resistance is very small compared to reactance. The XR ratio, if you remember, I have discussed, X is much higher than R. Okay, for high voltage system, it is a 400 kilovolt. X to R ratio will be of the order of 8 or 10, like that. Okay, if you go higher voltage, the ratio will increase. If you go for lower voltage, this ratio will decrease. If you come to the distribution level voltage, uh, resistance and inductive reactance, they will be of similar magnitude. If you go still lower voltage, towards still lower voltage, then resistance may even exceed the inductive reactance. Okay, that means since we are discussing the high voltage system, we are assuming that our system, our transmission lines are at high voltage. We can say that Z will be approximately equal to J times X. X means series inductive reactance. Is it clear? ঠিক আছে, বুঝতে পারছো কেন যে এক্স কে লিখছি আমরা জেড হিসেবে?
Yes, sir.
Okay. So V2 will be V1 minus JX into I. This J comes here because of the inductive reactance, J times X. Okay. And P minus JQ by V1 is the current. Okay. So this is the voltage, load and voltage. We are assuming that the generator and voltage is fixed. So what is the load and voltage? We can actually rearrange this here and can write V1 minus Q by V1 into X. V1 minus Q by V1 into X. It is shown in the phasor diagram here. And minus J P by V1 into X. Okay. The perpendicular component is P by V1 into X. Okay. Is it clear? So V2 is finally written in this way. V1 minus Q by V1 into X minus J P by V1 into X. All right. Now you see that what happens if P is changed. Let us assume that we are delivering a certain amount of power. Now, for some reason, keeping the reactive powers same, I want to draw more active power, or I want to deliver more active power to the load. Okay, this situation may happen. This type of situation may arise. So if you want to deliver more P, more active power, which component of phasor here? There is one component of phasor is Q by V1 X1. This is just opposing V1. Okay, this is the V1 phasor. And P by V1 into X. This is the phasor perpendicular to the V1 phasor. Okay, so if you want to increase the value of P, this perpendicular component is mainly changing. There is no change in the value of Q by V1. Am I right? Is it clear?
Yes.
Yes. Okay, so what happens if the perpendicular component is changing? What is basically changing? The delta is changing basically. Am I clear?
Yes, sir.
That means if you want to change active power P, then what will happen? Basically, the delta, that means phase angle between the two voltages, this will change. Okay. All right. If you want to deliver less power, then delta will be decreasing. If you want to deliver more power, delta will be increasing. That means active power variation is creating variation in delta. Okay, active power variation is creating variation in delta, and you'll see that not much variation in V. Okay, now assume that keeping P constant, I want to change Q, reactive power delivery I want to increase or I want to decrease. Say for the time being, I want to increase the reactive power delivery. Okay. So keeping P constant, if Q is changed, what is happening? Q is increased means this vector, that means which is opposing the vector V1 directly, that means 180 degree out of phase with respect to V1. If this is increased, then what will happen? This magnitude component, V1 is decreasing mainly. That means the magnitude component is basically decreasing. And since Q by V1, it is, this P by V1 is not changing, this component remains more or less same. That means you say that delta variation will not be much here, rather there will be variation in the magnitude component because Q by V1, this is directly opposing, or that means this component involving Q is directly opposing V1 vector. Okay, that means you can say that if reactive power is varied, basically this magnitude component will be varying. There will not be much variation in the phase component. Or you can say that voltage drop or voltage variation. Voltage variation is not due to phase angle. It is due to the magnitude variation only. That means when we say that voltage is, say, declared voltage is 230 volt, but we are getting 180 volt, means voltage magnitude change. We are not talking about the phase. That means this magnitude variation is basically due to the reactive power drawn by the system. That means between the active power and reactive power of the load, we can say that magnitude of voltage or voltage variation is mainly due to the reactive power, not due to active power. Is it clear? Is the point clear? What I want to explain here? বলো ভোল্টেজের ভ্যারিয়েশনটা হচ্ছে কেন? বিকজ অফ মোস্টলি দ্য reactive power variation, not because of the active power variation. Okay, কেননা P vary করলে যেটা হয়, this perpendicular component is changing. That means phase is changing mostly. Into if we change Q, then this in phase, that means the phase component rather, that is so totally out of phase basically. That is reducing the voltage. Q is more means there is more voltage drop. Phase angle change is not much. Okay, that means when you change reactive power, the magnitude of voltage will be mostly changing, not the phase. There will be, later on we shall see that there will be some change in the phase also. It is not like that the phase will not change at all. But here, to make the analysis simple, to keep the things simple, to start with, what we have done, we have totally ignored the presence of any resistance because that makes things easier to understand. That's why we can say that in high voltage system, basically what happens, obviously this is true for high voltage system. This will not be true for a distribution level voltage, distribution system. That will not be there. But basically, any change in the voltage, any control of voltage will be mostly at the higher voltage part of the system, not at the lower voltage part. Okay, when we want to basically control the voltage, all these things will be mostly done from the high voltage part of the system. At the lowest level, there is very little scope of doing this. That's why we are assuming that our system is at high voltage, because any control regarding the voltage variation we shall be doing by uh, doing something at the high voltage part of the system. Okay, so at the high voltage part, you see that if the active power is changed, then phase angle of the voltage is changed, and if reactive power is changed, mainly the voltage magnitude is changed. Is it clear or not? Bolo, is the point clear? Or it needs more explanation? Please answer. Could you get the point or not?
Here, during the consideration of impedance, we are not, why we are not considering the capacitive reactance?
Capacitive reactance. Where the voltage drop occurs, is there any voltage drop occurring at the capacitive reactance? That is from conductor to conductor. And if we show the equivalent capacitance, that we show from conductor to neutral, phase to neutral. So current is basically flowing through the conductor, not through the capacitance. Okay. Whenever the load current is flowing, where it is flowing? It is flowing through the conductor itself, then through the from generator, through conductor to the load.
Yes.
Okay, not through the capacitance. So there is no question of voltage drop in the capacitance. What the capacitances are doing, they, when they are charged, that means when the transmission line is charged, they basically supply the reactive power because they draw some current, charging current to it. That charging current means capacitive current. That capacitive current is responsible for the supply of reactive power to the system. We call it reactive power supply because in the system series reactance, there is some reactive power absorption. So if there is some reactive power absorption in the series reactance, obviously in the capacitive reactance, there will be some reactive power generation. So capacitor mainly is generating reactive power to the system. Okay. So with the variation in load, there will not be all much change in that reactive power supply. That's why we are not considering that here. Okay. When you are drawing more reactive power or less reactive power, there is more current flowing through the conductor or less current flowing through the conductor. That much. Not to the capacitor. বুঝতে পেরেছো?
Okay, sir.
That's why we are not entering capacitive reactance. Obviously, as you have mentioned, why we are not including that? Obviously, capacitors has some role to play with the voltage control of the department. How they are supplying reactive power. Okay, so they help the system to maintain voltage. But in this analysis, we are not taking that into consideration. We are assuming that capacitors are there, they will be supplying. But what is happening to the variation in what is happening due to the variation in load current? Because of the variation in load current, there is the voltage drop occurring in the system, and that voltage is dropping because of mostly the reactive power requirement. Capacitor যেই পার্টটুকু করতো সেটা তো এখনো করে যাচ্ছে, ঠিক আছে, তার কোনো চেঞ্জ হচ্ছে না. That's why we are not taking that separately now. Okay, they have some effect, but that effect does not depend upon the increase or decrease in load. সেটা লোডের উপর খুব একটা ডিপেন্ড করছে না. লোডের উপর কোনটা ডিপেন্ড করছে? কন্ডাক্টরে যে কারেন্ট ফ্লো করছে সেটা ডিপেন্ড করছে. সিরিজ কারেন্ট অফ দা, that means current through the conductor, that is dependent upon the load. Okay, so that means that is dependent upon the load means basically the reactive power consumption in the conductor is depending upon the load. Voltage drop in the conductor is depending upon the load. বুঝতে পেরেছো? তার জন্য আমরা এই ক্যাপাসিটরকে আপাতত কনসিডার করছি না, বিকজ whatever reactive power the capacitor were delivering previously, they will be supplying almost the same amount of reactive power. একটু ভেরিয়েশন হবে. কি ভেরিয়েশন হবে? যদি সিস্টেমের ভোল্টেজ ড্রপ করে যায় তাহলে রিঅ্যাক্টিভ পাওয়ার সাপ্লাইটা একটু কমে যাবে. দ্যাট মিনস ইট উইল ফার্দার অ্যাগ্রাভেট দ্য সিস্টেম ভোল্টেজ ড্রপ. সেই অ্যাগ্রাভেটিংটা আমরা কনসিডার করছি না আপাতত. বুঝতে পেরেছো?
Yes, yes, yes.
Am I clear?
Yes.
It is okay? Could you understand, everybody?
Yes, sir.
Okay. Now, so whatever we have observed here, you see that a change in P affects the perpendicular component of voltage that I have mentioned. Okay, change in active power demand has little effect on the magnitude of V2. Why we say that there is little effect? Because obviously, if there is a change in the perpendicular component, then total magnitude is, then that means the magnitude basically is the, you see that it is square of this component plus square of this component, then square root. Obviously, it has also some part, but you see that since phase angle difference is not much in power system, what is the phase angle difference? That is not very large. In, if you see the phase angle difference between the two end voltage of a transmission line, that is very small. Okay, 4, 5, 6, 10 degree like this. That means the series component is, or in phase component is mostly responsible for the magnitude of voltage, not the perpendicular component. Okay, so change in active power demand has little effect on the magnitude of voltage V2 at the receiving end. Okay, a change in Q affects the in phase component of voltage drop. As we have mentioned, this component is being reduced. Okay, the change in Q affects the in phase component. Therefore, what happens? Change in voltage magnitude is mainly caused by the reactive power. Or you can say that active power variation mainly causes phase angle variation, reactive power variation mainly causes magnitude variation. Or you can say that in the reverse way, if you change the phase angle, then active power flow will change. If you change the voltage magnitude, then mostly the reactive power will change. Okay. Obviously, আমি যখন এই ভোল্টেজ চেঞ্জের কথা বলছি, then we are talking about the permissible change. তার মনে হতে পারে যে ভোল্টেজ চেঞ্জ করলে তো অ্যাক্টিভ পাওয়ারও চেঞ্জ হয়ে যাবে, but you remember that in power system you are not allowed to vary voltage to that extent. Voltage কতটা ভ্যারি করা যাবে? Within the declared limit only you can vary the voltage. 5% of the supply voltage you can change. Then within that 5%, active power will mostly depend upon the phase angle difference. Reactive power will depend upon the magnitude of voltage. Okay. তারপরে what we can infer from this analysis, from this discussion, active power flow through lines can be changed by controlling the voltage phase angle. That means now you see that you want to, we have seen this, if you change the active power, then phase angle changes. So in the reverse way, you also can say that if you want to deliver more power through a transmission line, what you can do? You can arrange to change the phase angle difference. ওকে, আমি চাইছি যে এই লাইনের মধ্যে দিয়ে বেশি পাওয়ার ফ্লো করাবো, এরকম এরকম হতে পারে। কখন হতে পারে? ধরো there are two transmission lines. Okay, out of these two transmission line, I want that more power will flow through a particular line. Then what I should do? I can arrange to change the phase angle difference between the voltages at the two end of the transmission line. That will actually cause more power flow. That will actually affect more power flow through the transmission line. That means active power flow through lines can be changed by controlling the voltage phase angle. Okay, that means P and delta have a strong coupling. We have seen if we vary P, then delta changes. That means the coupling or the dependence basically between P and delta is very they are having a strong dependence. If you change delta, then P changes. If you change P, then delta changes. Similarly, what we have observed, reactive power flow can be changed by controlling the voltage magnitude. We have changed this. We have seen that if we change the reactive power flow, then voltage changes. So reversely, what you can say, if you want to deliver more reactive power, you have to change the voltage. That means reactive power flow can be changed by controlling the voltage magnitude. Sometimes you may have to control the active power flow, you may have to control the reactive power flow. So the mechanism will be to control the voltage magnitude in order to control the reactive power flow. So you will be controlling phase angle difference to control the active power flow. You will be controlling the voltage magnitude to control the reactive power flow. Coupling between P and V and Q delta are weak. That means P changes basically change delta, phase angle difference, not V. That means we can say that there is a coupling, there is a dependence between the active power and voltage, but that dependence is not very strong. Rather, it is a weak dependence. So coupling between P and V, it is weak, and coupling between delta Q and delta is also weak. So PV coupling and Q delta coupling, these two are weak. So why you are discussing this thing? These things are very, very important when we actually talk about the analysis control of power system. In any power system, later on you'll be seeing that many analytical tools in power system are utilizing these facts. Control of power system is based upon these facts. That means P and delta are strongly coupled, Q and V are strongly coupled. Coupling between P and V is weak. Coupling between Q and delta, this is also weak. Okay. This feature is extensively used for power system control and analysis. We will be observing this because in other courses also we will be studying. So you will be seeing that in any power system, the control of active and reactive power, they actually utilizing these facts, particularly when we are talking about the control of voltage and you can say frequency in power system. Okay, if we discuss about the voltage control, then at the high voltage part, this fact is very much used. If you talk about the frequency, obviously, then frequency, it is true. It is dependent upon that phase angle. Okay, active power is dependent upon the phase angle, and for frequency control, you have to control the active power. This is true irrespective of high voltage and low voltage. But for the voltage control, reactive power control, this analysis, this discussion is valid for the high voltage part of the power system, because at the low voltage part, as we have discussed in the previous discussion also, previous day also, that X to R ratio of low voltage system is much different from the X to R ratio of high voltage system. And this X to R ratio is very, very important for power system analysis, power system protection, and many other things. Okay. Now, how we can conclude this discussion, say, okay, regarding the voltage control and frequency control, let us conclude now in this way. Active power generation has to be controlled for controlling frequency. Is this statement clear to you that for frequency control, we must control active power generation? Why we say that? Because we have seen that if we change the load, that means that if we draw more power from the system, then what happens? The speed of the generator decreases. Speed of the generator means synchronous generator decreases. And in power system, till today, most of the generators are synchronous generators. At least 80% of the generators are synchronous generators, almost in every power system except very few. So we can say that for frequency control, what you have to do, you have to basically control the active power generation. Is this point clear to you? That for frequency control, you have to control the active power generation. Why? Because as we have seen with that single example, we have mentioned that when we are connecting more load, speed of the generator is decreasing. Means frequency of the system is decreasing, because speed of the generator is decreasing means frequency of generation is decreasing, means frequency of the system will be decreasing. Is it clear, this point?
Yes, sir. Yes.
Okay, then for controlling system voltage, reactive power flow has to be controlled. তাহলে তুমি যখন ভোল্টেজ কন্ট্রোলের দরকার হবে, সিস্টেমের ভোল্টেজটা উইক হয়ে রয়েছে, কম হয়ে রয়েছে, তাহলে কি করবে? ইউ হ্যাভ টু সাপ্লাই মোর রিঅ্যাক্টিভ পাওয়ার। কেননা লোড বেশি রিঅ্যাক্টিভ পাওয়ার ড্র করছে বলেই ভোল্টেজটা ড্রপ করেছে। এবার তুমি যদি রিঅ্যাক্টিভ পাওয়ার সাপ্লাই দিতে পারো, দেন ভোল্টেজ উইল ইমপ্রুভ। হাউ ভোল্টেজ উইল ইমপ্রুভ? এবার রিঅ্যাক্টিভ পাওয়ারটা তুমি যে সাপ্লাই দেবে, কিভাবে দেবে? You will be trying to supply this reactive power at a point which is as close as possible to the demand of reactive power. যেখানে রিঅ্যাক্টিভ পাওয়ারটা ডিমান্ড করা হচ্ছে, চাওয়া হচ্ছে, ড্র করা হচ্ছে, তার যতখানি কাছে গিয়ে রিঅ্যাক্টিভ পাওয়ারটা সাপ্লাই দেওয়া যায় ততটাই ভালো হবে, কারণ তাহলে ওই রিঅ্যাক্টিভ পাওয়ার ফ্লোটা লাইনের মধ্যে দিয়ে হবে না। ক্লিয়ার? কারণ লাইনের মধ্যে দিয়ে হলে পরে আবার ভোল্টেজ ড্রপের প্রশ্ন হচ্ছে, এবং ভোল্টেজ ভেরিয়েশন ইজ বেসিক্যালি ডিউ টু রিঅ্যাক্টিভ পাওয়ার। কাজেই যেই কম্পোনেন্ট অফ পাওয়ারটা ভোল্টেজ ভেরিয়েশনের জন্য রেসপন্সিবল তাকে আমরা চেষ্টা করব যাতে করে যত কম সম্ভব লাইনের মধ্যে দিয়ে সেটা ফ্লো করে। So it is always better to supply reactive power as close as possible, okay, to the demand where it is being made, okay, to the point where it is being made. Frequency control can be done from power plants only. This is important. You say, so what we have seen that frequency control, for frequency control, you have to control the active power generation. Where the active powers are there? Obviously, certainly, active power is generated at the power stations only. তাহলে for control of frequency, you must control the power generation. And from where you can control the power generation? Obviously, at no other location other than the power stations. তাই তো? কাজে পাওয়ার স্টেশন থেকে তোমাকে ফ্রিকোয়েন্সি কন্ট্রোল করতে হবে। প্রিভিয়াসলি মানে যে প্র্যাকটিস এখন চলছে পাওয়ার সিস্টেমে, মোস্ট অফ দ্য জেনারেটরস আর synchronous generator যেরকম বললাম, okay, they are connected to the high voltage part of the system and loads are connected at the lower voltage part. কিন্তু কি হচ্ছে, সিনারিও চেঞ্জ করছে। হাউ ইজ দ্য সিনারিও ইজ চেঞ্জিং? বিকজ উই আর গোয়িং টুয়ার্ডস রিনিউয়েবলস। those renewables generators are again now connected at the low voltage part of the system. কাজেই কি হবে, এর পরে পরে যেটা হবে, যত বেশি রিনিউয়েবল সিস্টেমে কানেক্টেড হবে তত দেখা যাবে লো ভোল্টেজ পার্টে অনেক বেশি জেনারেটিং ফ্যাসিলিটি ঢুকছে, ছোট 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 জেনারেটিং ফ্যাসিলিটি ঢুকছে। সো ফ্রম দেয়ার অলসো ফ্রিকোয়েন্সি নাও ক্যান বি কন্ট্রোল। ওকে, এই যে সিস্টেমের ফ্রিকোয়েন্সি চেঞ্জ করতে প্রিভিয়াসলি যেটা করতে হতো, প্রিভিয়াসলি নয়, ইভেন টুডে this has to be done from the high voltage part of the power system. Can high voltage part? Because large generators are always connected to the high voltage part. কেননা লার্জ জেনারেট হাই ভোল্টেজটা বেশি পাওয়ার হ্যান্ডেল করতে পারে, এই জন্য হাই ভোল্টেজ লার্জ জেনারেটর গুলো হাই ভোল্টেজে কানেক্ট করতে হয়। কিন্তু রিনিউয়েবল জেনারেটর, মেনলি সোলার, উইন্ড, দে আর ভেরি স্মল জেনারেটরস। কেননা ছোট 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 ডিস্ট্রিবিউটেড এনার্জি তো সেজন্য ছোট ছোট জেনারেটর হয়। They are to be connected at the lower voltage part. Unless you actually a very large vast field is needed there, যেখানে তুমি প্রচুর সোলার প্ল্যান্ট, প্রচুর উইন্ড প্ল্যান্ট লাগিয়ে অ্যাকুমুলেট করে তাকে হাই ভোল্টেজে কানেক্ট করতে পারো। Those things are rarely available. Rather, renewable generations are mostly distributed in nature and they are connected at the low voltage part of the system. কাজেই এর পরে পরে যেটা হবে, লো ভোল্টেজ পার্ট অফ দ্য সিস্টেম থেকেও ফ্রিকোয়েন্সি কন্ট্রোল করা যাবে, এরকম সিচুয়েশন সমস্যা তৈরি হচ্ছে। ওকে, voltage control can be done from power stations and transmission as well as distribution subsystem. তাহলে voltage controlটা কিন্তু on the other hand may be done from the power station. কি করে from power station? Because the generators, through the generators you can control the voltage. How? We shall see in our next class. We will see how from synchronous generators we can control the voltage. Not only from synchronous generators, voltage control is possible from the transmission substation as well as for distribution substation, because you may actually change the tap setting of the auto transformer, you may install some capacitor, you may install some static var compensator. There are other devices, they can control voltage, they can generate reactive power. কাজেই ওই ভোল্টেজ কন্ট্রোলটা ট্রান্সমিশন সাবস্টেশন থেকে হতে পারে, ডিস্ট্রিবিউশন সাবস্টেশন থেকে হতে পারে, and even it is possible from the power station as well. কাজেই পাওয়ার স্টেশন থেকে ফ্রিকোয়েন্সি কন্ট্রোল হবে, পাওয়ার স্টেশন থেকে ভোল্টেজও কন্ট্রোল করতে করা যাবে, কিন্তু at the same time voltage control is still possible from substation and transmission as well as distribution. তার মানে কি, ভোল্টেজ কন্ট্রোলটা হচ্ছে ডিস্ট্রিবিউটেড হতে করা যায়, ডিস্ট্রিবিউটেড কন্ট্রোল বলা যেতে পারে, but frequency control is rather concentrated at the central locations at the power stations. So it is all right, then it is possible to transmit active power over long distances. Is this point clear? You can transmit active power over a long distance. Say 500 kilometer দূরে তুমি active power পাঠাতে পারো, but you cannot do that in respect of reactive power. Reactive power cannot be transported to be generated locally. So is this point clear? কেন বলছি, কারণ active power যদি আমি পাঠাই তাহলে কি হচ্ছে, active power flow, since we are transmitting at high voltage, okay, you see that active power flow will result in phase angle difference only, not the magnitude difference. That means there will not be much voltage drop when you will be transmitting active power, but reactive power transmission will need voltage drop. Since it is involving voltage drop, you will not be transmitting reactive power. তার মানে আমি বলতে পারি যে active powerটা অনেক long distance এ transmit করা যেতে পারে. You can transmit active power over very long distance, but you cannot transmit reactive power over a long distance, because for reactive power transmission, what is needed? Voltage difference is needed. So if you want to transmit reactive power, you have to increase the voltage difference between the two ends of the transmitter line. That you cannot do after beyond a certain limit. So you cannot transmit reactive power. তাহলে কি করা যেতে পারে? You have to generate reactive power, because reactive power generation is possible from the substation at the transmission level and also at the distribution. So active power is transmittable over long distance. Reactive power is not transmittable. It has to be generated locally. All right. Then okay. So this much. So is this point clear? All the points I have discussed. So now you say whether whatever I have discussed here, it is clear to you or not. Bolo. At any point, if I have to clarify more, I shall be doing that.
No, sir, it's clear.
So basically, whatever we have discussed, we have seen what should be the basic method of controlling frequency and controlling voltage. What we have seen that the active power flow and phase angle, they are strongly coupled. Reactive power flow and voltage, they are also strongly coupled. So for controlling of frequency, you have to control, and also for controlling the frequency, you have to control the active power generation. Why active power generation? Because if there is more power demand, then frequency of the generator, speed of the generator varies. Okay. So active power generation has to be controlled for controlling frequency. Reactive power flow has to be controlled for controlling voltage. You cannot transmit reactive power over a long distance, but you can transmit active power over very, very long distance. কেননা active power flow করলে voltage magnitude ততটা তফাৎ হয় না. Mostly যেটা চেঞ্জ করে, that is the phase angle of voltage. কিন্তু reactive power flow করলে there will be variation in the magnitude of voltage. So what we shall do? We shall rather generate reactive power at the proper location, mostly at the substations, transmission and distribution substation. Reactive power can generate করব. Okay. All right. Is it clear? So if it is clear, then we shall conclude today, and the next class, Friday afternoon will be the next class. That means at 4:30 Friday. Okay. So we'll be regularly meeting every Tuesday at 11 a.m. to 12:30 p.m. Every Friday at 4:30 p.m. to 6 p.m. Okay. Books
Okay.
for this regarding the books, you will be basically what you can say. There is one book by Elgard, OI Elgard, on frequency control. This is a very, very good book. It is available in our library. Maybe it may be available in the free version, maybe available in the net also. You can search for energy system control like that. It is OI Elgard. Okay. Then another book is by Stevenson. A modified version of that is also available. That is Stevenson and Granger. Okay. That will be required for starting the other part, synchronous generator and stability portion. Okay. So stability, synchronous generator, these things will be better covered in Stevenson and Granger in this book. What is basically the original book with Stevenson. There is some more issues covered in the second version in the Stevenson and Granger. Okay, and for frequency control, it will be Elgar's book, O.I. Elgard. Okay, and covering both the issues, there is one Indian book available. There is so many books available. One is very popular, that is this Nagrath and Kotari. This book is very popular. You can see Wada's book also, no problem. Okay. There are other books also you can see. There's another book by Asfaq Hussain. That also is not bad. So you can study all these books. Okay. So any other question you are having? Well,
Sir, what is the name of the book by C.L. Wada? Wadaর বইটার নেমটা কি?
ওয়াদার বইটা এগুলো আসলে মুশকিল হচ্ছে যে বইটার নামগুলো তো কোনটা মনে রাখা হয় না। সিএল ওয়াদা ইজ দ্য অথার। ওকে, ওয়াই এলগার্ডের পাওয়ার সিস্টেমের একটাই বই রয়েছে সেটা। ওকে, দেন স্টিভেনসনের এইগুলো বইয়ের টাইটেল মনে থাকে না, ঠিক আছে? স্টিভেনসনস বুক, এলগার্স বুক অন পাওয়ার সিস্টেম, and then Nagrath Kothari has so many books, but in every book they have covered these issues. Okay, then and Wada's book. So name of all these books, actually title of all these books, it is very difficult to remember because okay. So you search net, and if possible, I shall try to give you the name also. Okay. Now let me call your name. Abhishek Majumdar. Abhishek Majumdar.
Yes, sir.
Then Aditya Rai.
Yes, sir.